Okay, let me get out of the way here. We're in Kinesiology 230, Chapter 4, Presentation number 5, talking about energy and mechanical and movement efficiency. And there'll be a little bit of a retread for a slide just to kind of take us back and put us back in perspective regarding the topic from an earlier presentation. But without ado, let's go ahead and get going. So here we are in that big list that we saw from earlier. We're all the way down here, energy and mechanical movement. We are almost done with this thing. So let's go ahead and get going. So mechanical energy is the ability or capacity to perform mechanical work. It's the work that quite literally our human body performs on a day-to-day basis. And we can classify this into two main broad areas, potential and kinetic. Potential being stored energy, kinetic being motion energy. And if we think of this in terms of how this operates, you'll see in a couple slides here, you have potential kinetic over and over and over happening in the body, and it's just a matter of how you use it. So a kinetic energy, we have linear and angular, and those should be terms that look very familiar to you. Linear, very straight ahead. Angular is more rotational. And for each of the above, the key element is the squaring of the velocity in the equation. So down here, I did a cut and paste. You have linear kinetic energy and angular kinetic energy. For the V is squared here, and that's your linear velocity. For down here, your W is squared, and that's your angular velocity, meaning how quickly the lever is moving about the axis. The takeaway here is this. If you have a small change, in velocity here or here, you're going to have a large yield in terms of power output. So I can't stress this enough when you talk about refining movement with your athletes or working with your people. You have this kind of ripple effect where when you refine in one area and you can allow somebody to move faster and articulate better and quicker, it translates into a greater power output later on. So with athletic movement, it's performed at higher velocity. We talked about this, and therefore it has a higher power output. I just want to kind of touch on this again and go back and forth in terms of if we look at what happens with athletes versus people in generalized fitness programs, it's a little bit different, right? Because most of the people that we work with in generalized fitness programs, they perform all their activities at lower speeds and they do not optimize power at all. And to a certain degree, if you get a little further to the right here, we start talking about rehab environments and you're working in physical therapy, many times you're just working on mobility and trying to work on deceleration for some of your people, as opposed to like having a high velocity or high power oriented activity, because you're just trying to put your person back together. And then eventually you get to the point where you do slower speeds and lower loaded movement patterns, and then you can work more into power. But it's different in terms of a spectrum. You have like it's almost continuum between athletes on one side and rehab people on the other side. It's just the nature of the people that we work with. So with power, we already talked about this, incorporates force as part of the equation. So therefore, when a person gets a little bit stronger, they will have the potential to be more powerful, but that does not guarantee it because you have to work on technique to make sure they are able to actually work an exercise or a movement pattern at a more powerful output. And this also comes down to just programming, right? You have to be good enough as a coach or good enough as a trainer or a physical therapist to know how to incorporate power into the equation and when it's appropriate to do so. So potential energy, we have gravitational potential energy, and it measures the potential to do mechanical work as a function of height. And if we look at a bowling ball just kind of floating up here in the air, you have this gravitational potential energy will be this bowling ball that's suspended above the floor. We do not know the full amount of potential energy. We know it's a bowling ball and perhaps it's 10 pounds. We have those two main details, but we don't know how high it is up from the floor. And that kind of matters, right? Because at 9.8 meters per second squared, which is gravity, that's one of the key parts of this equation where it's mass times gravity times height, meaning how far away from the floor that ball is falling. And that's going to matter in terms of determining how much energy is being created from the force of gravity pulling that ball down towards the floor. So your big calculation for gravitational potential energy is this: mass times gravity times height, and gravity is 9.8 meters per second squared. And notice it's per seconds squared, and that velocity component that you have there is a squared number, so it goes up exponentially. Every second that ball is falling, the actual energy it's going to impart is going to go up, 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 and up, almost exponentially. All right, moving on. Potential energy. It's kind of you had first, gravitational potential energy, now you have deformational energy. And it's the energy that's stored within the body. This is kind of what we talk about all the time. Athletic movement, or even movement in general, requires deformational energy to create force through the repetitive lengthening and contraction of muscle to create and then apply force. And the book goes into a stress shortening cycle, which has its place. And if we look at going from a straight toe press, and now we're talking about being more explosive and doing like a box jump like I did in a previous video, there was a stress shortening cycle as I lowered my COG and jumped up onto that box. That's what they're talking about. It's a quick shortening of the muscle, and then, I'm sorry, quick lengthening of the muscle and then quickly shortening it. Sorry, I did that. So that backwards, I'm getting a little tired. So with mechanical movement and efficiency, I can't stress this enough. You have this mechanical output that can be produced and created by the muscles. Well, the work that's created, it's based upon a given amount of metabolic input, meaning energy. And a great example you have is, we oftentimes talk with and work with athletes regarding getting stronger, being more explosive. And, I've been doing it for 20 years, but you couple that with proper technique to be able to get the greatest amount of yield. So you have a couple of things going on here. You're trying to get your athletes to have the greatest amount of work that they can create and then be able to apply that into the ground in the most efficient type of manner. So you really have to have this kind of transition mindset from what they're talking about in the book to working with athletes, where you have a stronger and more explosive athlete can create more force and do more work, and they have the ability to create greater amounts of deformational energy via the muscles, and they have the ability to be very efficient at delivering the force into the ground. And then, as per Newton's law, they can get an equal and opposite reaction out of the ground, and they'll get a greater yield for their efforts on both sides of the equation. So as a coach or a movement practitioner, you have to be skilled at being able to not only get your people to create more output, to be stronger and more explosive and more powerful, etc., based off of the metabolic input that they have, but they also have to have the equal and opposite reaction when they're delivering force into the ground to get the most yield out of the ground. So it's pretty complex, right? So with this, if you think of muscles as a series of interconnected rubber bands, every time we pull that rubber band or stretch the rubber band, it's storing potential energy, right? That's that terminology back here when we're talking about, when we scroll back so you can see it, we're talking about deformational energy here. And with deformational energy, we're stretching the muscle, deforming it, and then when you've elongated the muscle, you store potential energy, and then we rapidly contract and you apply force into a medicine ball, the ground, a bar, whatever it is, and it switches the force potential to kinetic. And in athletics and movement, we talk about the cycle of potential to kinetic over and over again. And this is a slow-mo rubber band. Potential energy is stored up in the rubber band. You can see it, he lets go, boom, and that becomes kinetic. The potential energy that's stored is elastic and becomes kinetic when they release the rubber band. A good way to describe kind of yield out of this is when you look at like low potential energy and power output to the left with greater loss of energy into the ground with every stride. The foot contact is also reducing the power component because it's a full foot strike and they're running with long levers. And it's very vertical, right? Sprinters to the right, they have a high deformational energy and they're running more efficiently, and they're also running with a smaller contact patch on the ground, which means less time on the ground, which incorporates that power component like we've talked about before. And then as a result, because of Newton's laws, we have higher ground reactive forces. So let's take a look at our slow runners over here. Just chugging along, flat foot. You can see all the energy kind of shuffling, how low their heels are relative to their knee. This guy's got a little bit higher knee recovery or heel recovery over his knee. Very, very low, very low. A lot of energy going in the ground. You can see the collapsing of the knee every time the foot strikes. There's hip flexion every time the hip strikes. Recreational runners, right? Now if we go back over here to Mr. Volt, I'll pause this while commercial. Okay, so we're all dialed up over here. We'll get this guy running. And again, we get back to this style of running where it's a much different animal, where they're running with short levers, heels up towards the butt. The contact patch on the ground is much smaller, right? You can see there really isn't much vertical deflection like they have with the recreational runners. The hips are moving, but they're not collapsing. The knee is different position as well. So what happens with this is, these folks to the right, they've trained quite some time to learn how to be very explosive and very strong and be able to apply force into the ground in a very short amount of time. And they also have the mechanical capabilities to deliver force in the ground and get as much out of the ground as possible. They have greater yield in the process than the folks to the left. See the difference right there. All right, guys, I'm going to sign off on this. I'm going to go to the next presentation.